right. Hey everyone. This is Miss Turk. Um, so what we're gonna do today is the 5.5.3 test. Okay. Unit 5, kind of like Unit 4, they're covering a lot of stuff that's very difficult in a very short period of time. So don't feel bad if you were confused in Unit 5. And I'm going to be omitting a lot of stuff and giving some pretty heavy hints for parts of this because I don't think that the text explains some stuff super well. So for question 1A, what's the most likely oxidation state of aluminum? This was not explained in the stuff that they gave you. I think they made it pretty clear. Group 1's oxidation state is 1 plus because they lose 1 valence electron. Group 2's oxidation state is 2 plus because they lose 2 valence electrons. They didn't talk much about group 13, which is where aluminum is. Group 13 has 3 valence electrons and it tends to lose all of them, meaning it'll have a charge of 3 plus. Okay, so it's losing negative electrons, so it has more protons than electrons. That's why losing electrons leads to a positive oxidation state. Okay, so positive 3 would be the answer to that one. For part B, you need to go to 5.5.1 and click on the FYI button, and they give you all the hints for oxidation states. Some things I want to emphasize. When an element is alone, its oxidation state is 0. Even if it's just bonded to itself, its oxidation state is 0. When it's bonded to something and you don't know the oxidation state, you can figure it out by looking at the things with the oxidation state that you do know. So for example, in MnCl2, chlorine is in group 17. It has 7 valence electrons, so it tends to gain 1 electron to fill its octet. And that, electrons are negative. So when it gains an electron, it becomes -1. So think about if those two chlorines were -1, what must the manganese be? Because all those charges need to add up to 0. Okay. This one's a little trickier. This negative symbol is not in the right spot. Think of it like this: MnO4, and this entire compound has a 1 negative charge. So this one is not neutral. So these charges, these oxidation states, need to all add up to -1. So remember, oxygen's in group 16, so it's going to be -2. So if these 4 oxygens are -2, what must the charge on the manganese be for everything to add up to -1? Okay, so you gotta have to work backwards there. For question 2A, you can omit that. And and then B, the half reactions, I'm actually gonna write them for you. And label the oxidation and the reduction reaction. Okay, so what we have here, the reason I don't want you to do this one is because they didn't make it very clear what the oxidation state of the nitrogen is, and it's not possible to figure it out based on what the book told you. So what I'm going to get, the information I'm going to give you, the aluminum is 0 and the copper is 0 because they're alone. Okay. The copper is bonded, and these two NO3s have a total oxidation state of -2. So to balance that out, this copper is +2. And over here, these 3 NO3s add up to -3. So this aluminum, to balance that out, is +3. Okay, so the aluminum goes from 0 to +3. The copper goes from +2 down to 0. Okay, so one of those things was oxidized and one of those things was reduced. The way I remember it is the one that was reduced is the one whose charge went down. Okay, reduces down. Aluminum's charge went up, 0 to +3, but copper's charge went down. It went from +2 down to 0. So when we write the half reactions, we don't deal with this, the NO3s. We just focus on the elements that were oxidized and reduced. Okay, so we have 2 aluminums, okay, becoming 2 aluminums with a +3 charge. Okay, so one of the half reactions was the 2 aluminums becoming 2 aluminums with a +3 charge. Okay, and then we had the 2 coppers, or was it 2 coppers? No, it's 3 coppers with a +2 charge, turning into 3 coppers with no charge. Okay, so those are the half reactions. Okay, the reason the charge is changed is because electrons were gained or lost. Okay, so the half reactions have to include those electrons. So these aluminums, their charge went up, okay? And the reason they became positive is because electrons were lost. And when you lose negative electrons, you become positive. So when these aluminum atoms became these two aluminum ions, electrons were given off. So I'm going to say plus E, negative, that stands for electrons. And think about how many electrons were lost. Well, each aluminum lost 3, so a total of 6 electrons were lost, okay? Um, Copper, on the other hand, copper's charge went down, so electrons had to be gained. So these coppers that were positive gained 6 negative electrons to bring the charge down to 0, okay? Because those 3 coppers were each 2 positive, so all 3 coppers each gained 2 electrons, and they all went down to 0. Okay, so those are your 2 half reactions. Now we need to label the oxidation reaction and the reduction reaction. Reduction means the charge went down, okay? And we see that's copper went from positive 2 down to 0. So this is the reduction. And oxidation, the charge goes up. And aluminum's charge went from 0 up to positive 3. So this is the oxidation. So you can see why these things go in tandem, why they're called redox reactions, which is short for reduction and oxidation. These are, or sometimes they're just called oxidation reduction reactions. They happen together. So the aluminum lost electrons and the copper took those electrons, okay? So in this equation, what was oxidized and what was reduced, that's pretty clear. The aluminum was oxidized and the copper was reduced. And then D you can omit. All right. And then this next one talks about these things happening together. So we can make an oxidation reduction happen, and if it's a spontaneous reaction, it'll just happen on its own, and that transfer of electrons can be harnessed to be used as a source of electricity, because that's what electricity is, it's moving electrons. So a flow of electrons is what we call electricity. Electrons are actually named after electricity. So we discovered electricity and then later on discovered it was electrons flowing. That's what electrical current is. So you can set up a reaction between two things and get the redox to start going, the oxidation reduction, and use that electricity, okay? So it's asking you which, if you have these two metals reacting, which one's oxidized and which one is reduced, okay? So what you need to do is look at 5.2.1, page 11, and use the chart. And the one with the more positive reduction potential will be the reduced one. So you can see what that chart has is an equation of zinc being reduced and an equation of magnesium being reduced. And the one with the more positive reduction potential is the one that will actually be reduced. And the other one will be oxidized, okay? So you need to write the half reactions for those, okay? So the one that's going to be reduced, you're going to set up like this, okay? So you'll have it in its ionic form, okay, with the charge. So just look on, essentially you're going to write down exactly what's on the chart because the chart shows that element being reduced. So whichever one's going to be reduced, kind of write it like this. It's not copper, it's zinc or magnesium, okay? So that will be the half reaction for the reduction. And then the one that's not going to be reduced is going to be oxidized. So you just look at the chart and flip that reaction the other way, and that represents oxidized, okay? To figure out which one's the anode and which one is the cathode, you just look at 5.2.1, page 8. This part you can omit. And this part I'm just going to tell you what kind of electrochemical cell is this. So there's two types of electrochemical cells. There's galvanic cells, which are the ones that happen spontaneously, and there's electrolytic cells, which don't happen spontaneously, which require that you add energy. And like I said, this one is spontaneous. It just happens on its own. We can use this as a source of electricity because it's just going to happen and electrons are just going to flow, okay? So this one, I'm just telling you the answer here. It's a galvanic cell because the reaction is spontaneous. If the reaction is not spontaneous, it requires an input of energy, and we call that an electrolytic cell. So you can force a reaction to go essentially the wrong way, the non-spontaneous way, if you add energy, okay? And that's what we have here, okay? So for part B, it's silver and nickel, and they're telling you that silver is oxidized and nickel is reduced. And you'll notice that doesn't match the chart because silver actually has the more positive reduction potential from the chart. So this shouldn't happen this way, but it's a non-spontaneous reaction. It requires an input, okay? So they're telling you silver is oxidized, and they're telling you nickel's reduced. So for the half reaction, just look at the chart and copy down what it says for nickel on the reduction chart. And then for silver, just reverse what it says, okay? So for silver, just reverse what it says, and that's silver being oxidized. To figure out which one's the anode and the cathode, once again, look at 5.2.1, page 8. For number 3, you can omit that. And number 4, I'm just telling you the answer. This is an electrolytic cell. The reason is a couple of things, but it's because overall the voltage is negative, so the reaction's non-spontaneous. This is not going to happen on its own, okay? You have to add energy to do it, okay? Let's see. So we have a redox reaction down here, okay, for question 4. Write the half reactions and make sure it's balanced for atoms and number of charge. So I'm going to actually tell you most of the answers to this one. So we can see sodium is going from 0 to 1 positive, and copper is going from positive 2 down to 0. So copper is being reduced. Okay, so I'm going to do copper first. The reduction is Cu2 plus going down to Cu, okay, like that. And for Cu to do that, it would need to gain 2 electrons, okay, because those 2 electrons will bring that charge down to 0. The oxidation is the other one, okay? So the sodium is being oxidized. Its charge is going from 0 up to 1, okay? So we have sodium going up to Na1 positive. And when it goes up, it gives off an electron, okay? And it said we need to balance this for charge and electrons. What they mean is this copper needs to take 2 electrons. So it needs, in order to do that, it needs to react with 2 sodiums to give off 2 electrons, because each sodium only gives off 1. So that's what they mean by balancing it for number of atoms and charge, okay? Then multiply each half reaction by the correct number in order to balance the charges for the 2 half reactions. We already did that. So that's been done. And then for part C, add the equations to get a balanced equation. So what you're going to do is take these two, and the electrons, because they're before and after, are going to cancel out. And so what you have before is 2Na plus Cu2 plus before the arrow. And then let's add up like I said, these cancel out, the electrons. And then after the arrow, we have Cu and 2Na1 plus. Like that. Okay. All right. Question 5, stoichiometry. Stoichiometry is how you say this word. Okay. Stoichiometry is essentially the mathematics of the kind of ratio that we can derive from chemical equations. Okay. So this is going to bring back in moles that we talked about back in the previous unit. Okay. So we have an equation, and we're going to use that to do some math. So what this equation is saying is that for every 1 molecule of C3H8, it needs to react with 5 molecules of O2, and you get 3 molecules of CO2 and 4 molecules of H2O, okay? In the lab, we don't deal with individual molecules for obvious reasons. They're too small. So we scale up individual molecules, and we batch them into groups that we call moles, okay? A mole is like a dozen, but it's more things. So just like 1 dozen of these needs 5 dozen of these, and you'll make 3 dozen of these and 4 dozen of these, we can scale that up even bigger to a mole. A mole is not just 12, a dozen is 12 things. A mole is 6.02 times 10 to the 23rd things. So for every 1 mole of this, you need 5 moles of these, and you get 3 moles of this and 4 moles of this. And a mole is enough molecules. It's a big enough number that it's enough that we can see it. So if you were to get a mole of this, you could actually see it. It's enough molecules that we can actually work with it in the lab. So that's why we deal with moles when we're in the lab. So what it says in the first question is how many moles of Cr2 are produced from 5 moles of O2, okay? So It's kind of obvious on the front that from 5 moles of O2, you get 3 moles of CO2. It's kind of obvious, but I'm going to show you how I would do it mathematically if it wasn't that obvious, okay? So we would set up a little dimensional analysis problem. We start with 5 moles of O2, we put it over 1, throw moles of O2 under the bus, okay, and we want to get to moles of CO2. And then you look at the coefficients in the equation to get what we call the mole ratio. That's the numerical ratio of CO2 to O2, okay? So the numerical ratio for every 3 CO2s, we need 5 O2s. For every 3 moles of CO2, we need 5 moles of O2. So it's a 3 to 5 mole ratio. Okay, and then any unit on the top and bottom cancels out. Multiply straight across the top, you get 15 moles CO2. Multiply straight across the bottom, you get 5. 15 divided by 5 is 3 moles CO2, which is, we knew that anyway, but okay. The problem is, in the lab, we can't measure moles. Moles is enough that we can see it and work with it, but we don't have like a scale that can measure out 5 moles of O2, okay? What we do have is a scale that measures in grams, okay? So when we deal with grams, we have to do a quick grams to moles conversion before this and a quick moles to grams conversion after this. In order to figure out the grams of what we're starting with and ending with, which is more useful in the lab, okay? So this is saying how many grams of CO2 are produced from 5 moles of O2. So I'm going to start the same way, but instead of stopping here at moles of CO2, I'm going to add on another conversion to get to grams. Okay, so I'm going to throw moles of CO2 under the bus and put grams of CO2 up here, okay? So this is what we did in the last unit, okay? This is called the molar mass. So you look on your periodic table and you add up the mass of 1 C and 2 O's, okay? And that's the number of grams in a mole. So if we were to add up 1 C, which is 12.0, and 2 O's, carbon actually, probably on your periodic table, it's 12.01. And then 2 O's, so you have 12.01 plus 16 from one oxygen plus 16 from the other oxygen, you get 44.01 grams for every mole, okay? And then cancel moles of O2, cancel moles of CO2, multiply straight across the top, multiply straight across the bottom, and do top divided by bottom, okay? In part 3, they're asking us to start with grams and end with grams. So in this one, we're going to have 4 fractions because we've got to get from grams of O2 to moles of O2. Then we get to moles of CO2. Then we get to grams of CO2. So we're going to start out with 128 grams of O2 over 1. Throw grams of O2 under the bus and put moles of O2 on up here, okay? And this will get us from grams of O2 to moles of O2. The molar mass of O2, look at your periodic table. Each oxygen is 16 and there's 2 of them, so it'll be 32 grams for every 1 mole, okay? Now we're going to throw moles of O2 under the bus, and we're going to do like we did up here. We're going to go to moles of CO2. And whenever you see moles over moles, that's the mole ratio from the equation. It's 3 to 5, okay? And then we'll add on like we did here to get to grams of CO2, like that, okay? So cancel grams of O2, moles of O2, moles of O2, moles of CO2, moles of CO2. So multiply all the way across the top, multiply all the way across the bottom, and do top divided by bottom, okay? So this type is the type that's really useful in the lab because it tells you how many grams you need to start with and how many grams you're going to get in the end, which that we can weigh out on a digital balance. So this is the most common type of stoichiometry you're going to see. So stoichiometry is essentially a type of dimensional analysis, which we talked about in the last unit. Dimensional analysis is a way of converting units. Stoichiometry is a particular type of dimensional analysis that involves a mole ratio from a chemical equation. Like it involves a mathematical ratio from a chemical equation. All right, part 4, you can omit that. The next part you can omit, and the next part you can omit, and question 6 you can omit that as well, okay? because I feel like a lot of this was just pretty overwhelming. All right, so hopefully that's helpful. So that's it for 5.5.3 test.